5. This lecture is more or less a setup lecture, okay, for the rest of your modules, okay, which will deal with graphs. Okay, so today there will be lots of definitions and terminologies, okay, so it might be a bit more boring. Okay, so just some admin stuff. So some more details on your written quiz 1. Okay, there are 3 sections to your midterm. So there are 9 questions in total. Okay, so first section is analysis section. So I just give you some statement. Okay, then you're supposed to prove whether it's true or false. Okay, so section 2 is basically more advanced understanding of your data structures and algorithms taught. And then section 3 is application questions. Okay, so the material is from first lecture until this lecture. Again, tutorial 1 to tutorial 4. Okay. Past year quizzes has actually been put up already. Okay, if you look at the IDLE folder, file folder, okay, I have actually put up a zip file of past year quizzes. So you can take a look at that and try it out. Also, I have already posted the assignment of the students to the different midterm venues. Okay, so you can also look at that. Please remember which venue you're supposed to go to, okay, on Friday. Okay, so outline for this lecture. So today I will introduce one more data structure called the union find disjoint set data structure, which you will need to use later on, okay, when we deal with minimum spanning trees. Okay, after that I will talk about the 3 basic graph data structures we'll deal with for the rest of this course. And in order to do that, I will do a very hopefully quick review of graph terminology, so that might be the slightly boring part. Okay, so like I said, this lecture is more or less a setup for the rest of the course. Okay. Okay, so let's look at the first data structure we'll deal with today, which is the union find disjoint set data structure, or the UFDS. Okay. So we'll revisit this again when we deal with minimum spanning trees. Okay, basically what's a union find disjoint set? Okay, union find disjoint set is basically a collection of disjoint sets okay, disjoint sets. Okay, so you can do a few things given a set of disjoint sets, a collection of disjoint sets. Okay, you can union 2 disjoint sets when needed to form one set. You can find out which set an item belongs to. Okay, and you can check if 2 items belong to the same set. Okay, so it's quite a simple data structure. So let's look at this. Okay, let's go to Visual Algo. So here's an example of a UFDS, a union find disjoint set. Okay. So in this union find disjoint sets, how many items are there? There are actually 9 items. Okay, there are 9 items, right? So you can say I'm just labeling them from 0 to 8. There are 9 items. How many disjoint sets are there? There are actually 3 disjoint sets. Okay, so this is one disjoint set, this is one disjoint set, and this is one disjoint set. So there are 3 disjoint sets in this collection. Okay, and you can see that more or less each disjoint set is it's sort of organized in a tree. Yeah, it's organized in a tree. So let's see. First disjoint set, what are the items here? 0, right? And I have 1, right? I have 2, right? I have 4, right? And I have 3. Okay? So the root, okay, of the disjoint set is also called the representative item. Okay, it's called the representative item. So for the second one is what? I got 5, I got 7, then 6, right? 6 is the representative item. Okay, for the last one here, there's just 1 item in the set, which is 8. So 8 itself is the representative item. Okay? Okay, so given this union find disjoint set, how do we represent it? How do we represent this disjoint set? Basically, we just use an array. Okay, an array of size n, if you have n items. Okay, so how do you show this relationship? How do you show this relationship? What we do is this. Okay, let's say the array is called P, okay, of size n. So Pi, okay, this index I will refer to item I. Okay, refer to item I. So Pi stores what? The parent of I. The parent of I. So it stores some value j. Okay, so you just need one array. One array. Okay, so for example, let's say I want the parent of 0. What's the parent of 0? If you take a look at this disjoint set. 0 parent is 2, right? Correct? Yeah. So P of 0 will be 2. Okay, what about the parent of 1? 3, right? Yeah. Okay, then what about the parent of 3? 3 has got no parent, right? Is the representative, is the root of that tree. So basically, you just put back itself. So parent of 3 will be 3. This is how you identify that some item is the representative item of the set. If P of I equals to I, okay, that means it's the representative item. Okay. So, how do I represent this entire UFDS? It will be like this, right? E will be 2, 3, 3, 3, 3, 6, 6, 6, 8. Correct? Correct. So I label this as the indices 1, 2, 3, 4, 5, 6, 7, 8. Correct, right? P of 8 is 8 itself. P of 7 is 6 because that's the parent of 7. P of 6 is 6 itself is the representing item. P of 5 is 6, correct. P of 4 is 3, correct. P of 3 is itself 3. P of 2 is 3, correct. P of 1 is 3. P of 0 is 2. Yeah. So you just use one array, and then this is how you organize, how you represent this entire UFDS. Okay? Then? Okay, so let's look at the different operations that you can perform on this data structure. There is find set. Find set. So given some item I want to find the set it belongs to. Okay, so what I mean is that when I try to find the set that item belongs to, it will return the representative item of that set. Okay, it will return the representative item. So let's say I want to find set 3. What will it give me? It gives me back 3, right? Because 3 itself is the representative item. Okay? So, to find set 3, I'll just return 3. Okay? Now, what if I want to find set 0? What happens? So, I go to index 0, right? So, I go to index 0, I look at the parent. The parent will be 2, right? So I go to the parent, look at its parent again, correct? And that parent will be 3, right? So once you hit 3, then you see 3's parent is 3, so 3 is the representative item. That's when you stop. You just return that representative item. Okay, so what you do is that you just recursively call Pi on the parent until you hit the representative item. Okay, that's the idea. Okay, but that's not the end. Okay, so there's an important step here when I do find set. So you will trace, right? You'll see that if I start from 0, I go 2, I go 3, correct? Yes? And then I know that representative item or the set that 0 belongs to is 3. But as I am traveling up this path from 0 to 3, I will flatten the path. Okay, this is called the path compression heuristic. Okay? So what you do is that you will place everything along this path, every vertex along this path directly underneath the representative item. Okay, it's called path compression. So you see, after I do this, okay, 2 already belongs under 3, right? So now I just put 0 directly under 3. So you flatten the tree. So in UFDS, I want to make sure that every tree is as flat as possible. Is as flat as possible. Okay. Oops, wait. Okay, let me go back. Okay, so let me show you. Okay, I've shown all these. Oh, yes. Basically, you can see that the disjoint set forms a forest of trees, right? You have multiple trees in this, so it forms a forest of trees. Okay. Yes, I've shown you this. Okay, I've shown you this. Okay, find set. So let's look at the pseudocode for find set. Okay, let's look at the code for find set. Okay, so this is how I perform find set recursively. Okay, so find set, you pass in I, okay, and then you check if the parent of I is equals to I itself. Okay, parent of I equals to I itself. That means that it's a representative item. So you just return this representative item. Okay, otherwise, it's not the representative item. You recursively call find set on the parent of I. Okay, and then what is returned here must be the representative item, right? Right, you store it in this variable, and then you simply set I to be directly under this representative item. Okay, then you continue returning the representative item to the previous caller. So it's a recursive procedure. Okay, yeah. So the idea is here, I start from here, 0. So 0 is not the representative item, correct? Because P of 0 is 2. And then I go to, P of 0 is 1. Then I go to 1, right? 1 is still not representative, then I go to 3, or 3 is the representative item, right? So I'll pass back 3 here, 3 to 1, then set 1 to be directly under 3, which is, it is already directly under, no problem. Then I'll pass 3 down to 0, and set 0 to be directly under 3. Yeah. Okay. So that's how I get this. Okay, so you flatten the path. Okay, now some of you might try to do this. Okay, so this is just a public service announcement. So some of you might try to do this. Instead of having all these, right, 3 sentences here, just instead of these 3 statements, I just make it 1 statement. Okay, P set I, then recursively call find set on P dot get I. Okay, you'll find that this won't work. This won't work. Why? Because you would expect that P set will return the item that is stored at I, right? Correct? Here I am setting I to be whatever is returned by find set, correct? Then you expect that P set will return this, but it doesn't. Okay, it doesn't. It actually returns the element that was previously there before you set it. So you will get the wrong answer. Okay, so don't use this. Okay, don't use this. Okay. Okay, next is same set. Okay, let me go back to my example. Okay, next operation is same set. Test whether 2 items in your disjoint set is in the same set. Okay, it's in the same set. So, well, the idea of same set is quite easy, right? So if I have got 0 and 7, if I is 0 and then j is 7, are they in the same set? You just eyeball it, they are not in the same set, right? Right. So what do you do? How do you test whether they are in the same set? What you do is just call find set on 0, find set on 7, check whether the representative item is the same. If it's the same, they are in the same set. If it's not the same, then they are not in the same set. Okay? So it's all 0. Oh, 0 representative item is 3, 7 representative item is 6. So 3 and 6 not the same. So they are not in the same set. Okay? Let's go back here. Okay, so another example here. Find is same set 0 and 4, which is not true, right? Because representative item of 0 is 1, representative item of 4 is 3. So 1 and 3 is different. Okay, so very simple. The same set is just like return find set I equals find set j. Okay? So you'll see that in the same set code, I call find set, right? So in the same set, we also do path compression, right? So you see that path compression is done in a lot of places, okay? Next, union set. Okay, let's go back. Third operation we can do, to union two sets, okay? To union two disjoint sets. Okay, for example, I can say union I is 1 and then j is 5. Okay? Never mind. Let's not do 5. Let's do 8. Okay? So union 1, 8. Union set 1, 8. Union set 1, 8. What am I doing? I'm taking the set that 1 belongs to, right? Which is basically this set. Right? And I'm taking the set that 8 belongs to, which is this set, and I'm trying to make them into one set. Okay? So in this case, we have another heuristic that we will use. Okay, it's called union by rank. Okay, so union by rank, what I mean is that I will take the shorter tree, okay, the shorter tree, which is given a certain rank, to put it under the taller tree. Okay, so this is called the union by rank heuristic. Okay, so why do I do that? Why do I put the shorter tree under the taller tree? So the idea is that if I put a shorter tree under a taller tree, I don't increase the height of the resultant tree. Correct, right? If you think about it. Yes? So for example, let's say the taller tree height is h. Then the shorter tree must at most be h minus 1, correct? I place it directly under the representative item of the taller tree. The resultant tree is still h, right? It won't increase to h plus 1. Right? So that's the idea of union by rank. Okay? So in this case, what I do? In union set, I first find the representative item of I and find the representative item of j. Okay, so if I is 1, representative item is 3, right? So if j is 8, then of course 8 itself. And then you'll see that, this is taller. Okay, this set is taller than this set. So I will place 8 directly under 3. Okay. So, 3. Yeah, okay. So place 8 directly under 3. Okay, so what if it's the case when they are both the same height or the same rank? So if it's the same rank, then you can place anyone under anyone. Okay, but we have a certain convention here. Okay, the convention is this. So what I do is union set ij, correct? So I will place the left one, this is the left, under the right. So this is the right. Okay. So place the tree that I is in directly underneath the tree that j is in. Okay. If they are both the same height, same rank. Okay, that's the convention. Place the left under the right. Okay, so let's go back to our union set. Okay, now that in union set, we need to know sort of the height of the tree, right? We need to know the height of the tree, then we can determine whether one is taller than the other. Okay, so in here, in this heuristic, we call the height, we don't call it height, we call it rank. Okay, because it's not actually, what we are computing is not actually the actual height of the tree. Okay, it's just an approximate value. Okay, so we call it the rank. And we need to use another array, okay, called the rank array, that stores the rank for every item, okay, for every item. Okay. So I have another array, integer array called rank. So rank I will store the upper bound, it's called the upper bound, okay, of the height of the subtree rooted at I. Okay, it's like the P. P of I stores the parent of I. So rank of I here stores the upper bound of the height of the subtree rooted at I. Okay, so it's just the upper bound, it's not the actual height. Okay, so we call this the rank. Okay. Okay, let's look at the union set code. The union set code is quite simple. So here I will call union set on I and j. First, I check whether they are in the same set. Okay, check whether they are in the same set. If they are in the same set, then of course I don't need to union them, right? They are already in the same set. Okay. Otherwise, I find x the representative item of I, and find y the representative item of j. Okay. And I check what is the rank of x, what is the rank of y. Okay. So I say get rank, rank dot get x, rank dot get y. Okay. If rank of x is bigger than the rank of y, means that it's sort of taller than x is taller than y, right? So I will place y directly underneath x. Okay. So set the parent of y to be x. Okay. Otherwise, means it's smaller or equals to. So if it's smaller or equals to, then I just set the parent of x to be y. Okay. Place the left one under the right one. Okay. And then after that, I need to update my rank. For the case of what? For the case of when they are equal height. Okay, equal rank. So we check. If rank of x is equals to rank of y, okay, then I will increment the rank of y, okay, to be plus 1. To increment it by 1. Okay, then? So, here again, example here. Union set 0, 2. 0 representative item is 1, right? 2 representative item is 2, right? So you can see that here, x will be this one, y will be this one, right? Then rank of x, is it bigger than rank of y? Yeah, rank of x here currently is 1. This one, if they are not recorded, they are all 0. So at the beginning, you just set the rank of everything to be 0. Okay? So this is 1, this is 0, so x is taller than y, right? So I place y directly under x. Yeah, so I just do this. Okay? So you have this. So when I place it under, the rank doesn't change, so I don't need to update it. Okay, next one, the else clause. So example of the else clause is when I do union set 3, 4. Okay? So here x will be 3, y will be 4. Yeah? And then you see, oh, both are the same rank, both are 0 rank. Okay, so my convention is I will just place the left one underneath the right one, right? So x will be placed directly under y. Okay? So it becomes this. 3 will be placed under 4, and I will update the rank of 4 to be 1 now, to be plus 1. Okay? Okay, so far okay, right? Not that difficult union set. Okay, so one observation, you see that rank only ever increases, it never decreases. So we don't update the rank when we do path compression. You know, we use path compression almost everywhere, right? And in fact, here I also call find set in the union set code, so path compression is happening everywhere. But we don't update the rank, we don't minus the height. Okay? Because it's just an approximate value. Okay? It's just an approximate. You don't want to spend time updating it to be very accurate. Okay? Okay. So finally, I've shown you all the methods. Okay, so I show you the class. I do it in reverse. Okay, this is the union find class. Okay? So in this union find class, I have 2 array lists. Okay, representing my P array and then my rank array. Okay? So I have this constructor union find n. N means that I want to initialize it with n number of disjoint sets at the beginning. Okay? So I will initialize my P and then initialize my rank, and then I will for loop. So I add I from 0 to n minus 1 into P and then set the rank to be 0. Okay? Okay, so union find 5. So I create 5 different disjoint sets at the beginning. Okay, 0 to 4. Okay, so basically that's about it for UFDS. Okay, so that's the basic. So we won't go into more details. Okay, analyze what is the time complexity of each of those operations, a same set, find set, or union set. Okay, but what I want to say is this. Okay, all these operations, all those operations, is same set, find set, union set. Okay, runs in time big O of alpha n. Okay, what is this alpha? It's a sum function. Okay, which is called the inverse Ackermann function. Okay, so if you have used the two heuristic, okay, union by rank and path compression heuristic, then this inverse Ackermann function is actually a function that grows very, very slowly. It's much more slower than even log function. So for all practical purposes, you consider that any of those functions, right, run in constant time. Okay? Why? Because after some time you can imagine that all the trees are just one level. So each of my operation is just like one constant operation, right? Yeah. So you can imagine is that. Okay? For all practical purposes, it's one time. Okay? So I want to analyze it. It's actually quite hard. Okay. Okay, now let's do some exercise. Let's do some exercise on Visual Algo. Okay. Okay, imagine that I have created 6 disjoint sets, so 0 to 5. Okay. So can you give me a sequence of union set operations or find set operations that will give me this left subtree here? Okay, let's go. Let's try, let me create 6. Okay, initialize it with 6. That's 0 to 5. So what do I want? I want this. Okay, everything under 0. Okay. So let's go. Can you all tell me how I can get this? Okay. Let me demo. At the beginning, I just call this 1, 0. Union set 1, 0. So at the beginning, the rank are all 0, right? Because I mean you initialize it to 0. So when I say union set 1, 0, you'll check that, okay, 1 and 0 are their own representative item. They're both rank 0. So what do? The convention is what? Place the left one under the right one, right? So I place 1 under 0, which is what I want. Okay. Then after that, I can just keep calling union set 0, 2, 0, 3, 0, 4, 0, 5, right? Because now 0 is this tree that 0 belongs to is the taller tree now, right? Everything else is 0. Then they will all be placed under 0. Okay. So just union set 0, 2. So 2 will be placed under it. Union set 0, 3. 3 will be placed under it. Okay, union set 0, 4. And then union set 0, 5. Okay, so now everything is underneath 0. Yes. Yeah? So this is not the only way to do it. There are also other ways. Okay, you can call find set or compress the path and things like that, then you can get this. Okay? You can get this. So this is just one way of doing it. Okay, let's go back. Okay, so this is the first exercise. Second exercise. Now, given 8 disjoint sets, okay, give me this tree here. How do I get this tree here? Oh, this is quite you can see that it's actually quite a tall tree. Okay, meaning that if you want to create this, you cannot call a lot of find set operations, a function call, because find set will compress the tree. Okay, so this one you have to do it quite carefully in order to get this. Okay. So let's see. How do I do it? Initialize 8 items. Okay. So you all look at the lecture notes. Okay. So I can't show you the picture here. So you all look at it. Okay, so what do you do now? What can I do in order to get that particular UFDS? That particular tree. Can I start by creating trees of height 1 or rank 1? Can, right? I start by creating trees of rank 1. Okay. So first I'll say union set. Oh, what do I need? Let me go back here. Okay. So first I put 0 under 1. Okay. So sort of like I'm creating all the subtrees, right, in that final tree. Then after that I put 2 under 3, right? Yeah. Okay. Put 2 under 3. Then I'll put 4 under 5, right? Just put 4, 5. And then I put 6 under 7. Okay. Then after that, what do I do? Let's go back here. So I've put 1 under 0, 3 under 2, 0 under 1, 2 under 3, 4 under 5, 6 under 7. Okay. Now what do I do? So, well, number 1, I can do this. I can create this one, right? And then also create this one, right? Right. So I can place 1 under 3 and then 5 under 7. Yeah. Okay, let's do that. 1 under 3, 5 under 7. So 1, 3. 1 and 3, both of them are the same rank. So convention is place 1 under 3. Next, 5, 7. 5, 7, both same rank. Place 5 under 7. Okay, now finally, I need to put 3 under 7, right? Same thing, they are both the same rank. So I just do this. 3, 7. Okay, union set 3, 7. So place the like that. Okay, so that's how you get it. Okay. Okay, so there are more interesting things you can do. Okay, you'll look at it during the tutorial. Okay, so basically this is your UFDS. Okay, any questions on UFDS? Not that hard, right? Quite simple data structure. The idea, right? It's quite simple. Okay, so now we have gone through UFDS. We finished UFDS. So let's go to graph. Okay, so this sort of, like I say, this is set up for the rest of the module. So I have to go through a lot of terminologies and stuff like that. Okay, so please don't fall asleep yet. Okay. Okay, graph terminologies. And basically, what's a graph? Drink some water. What's a graph? What's a graph? A graph is basically an extension of what you have already learned. It's an extension of tree. Okay, or you can say it's a generalization of a tree. Okay, so in a tree you have what? You have your vertices, right, and then you have the edges, right, connecting them and things like that. So, same thing, in a graph, you have the notion of vertices, you have the notion of edges, you have the notion of direction of edges, and then you also have notion of the weight of the edges. Okay? So, the difference between the trees that you have learned so far, okay, between binary trees or binary search trees you have learned so far, and a general graph is this. Okay, in a general graph, there's no notion of the root. There's no notion of parent-child relationship or ancestor-descendant relationship. Okay, so for example, this graph here given below here, you can see if you take a look at it, I know this is what? It's a binary search tree, right? It's a binary search tree. Then I know that 15 is the root, and then 6 is his left child, 50 is his right child, and so on and so forth, right? And 5 is an ancestor on the left subtree of 15, and so on and so forth. Correct? Yeah. But then in the general graph, I can simply draw this entire thing like this. Okay, oops. Let me use this. Okay, I could have just drawn it like this. 15. Oops. Where did I have this? Erase all. Okay, 15, 50, 23. Okay, this is 23, yeah. Okay, 71, 6, 4, 5. I could have just drawn it like this, right? Then if you take a look at it, can you see this relationship of where's the root, where's the parent child? You can't see it, right? So in a general graph, it looks like this. Okay? So this is still a tree. Okay, this is still a tree. If you take a look at, if you view it as a general graph, it's still a tree, but it's an unrooted tree. Okay, it's an unrooted tree. There's no notion of where's the root. So when you have no notion of where's the root, then you have no notion of parent-child relationship and all that. Okay, can? Oops. Okay, so the graphs we'll be dealing with are basically simple graphs. Okay, simple graphs. They consist of a set of vertices. Okay, so and 0 to n, choose two pair of edges that will connect these vertices. Okay, so basically this. Okay, all these circles and the numbers are basically your vertices. Okay, so vertex usually we just label it from 0 to v minus 1 if you have v vertices in your graph. Okay, and then you can have undirected edges that connects the vertices. Okay, so for example, this undirected edge connects 0 to 3. Okay, so you will say that 0 is a neighbor of 3 and also 3 is a neighbor of 0. Right? Because in an undirected graph, I can go from 0 to 3 and from 3 to 0. Okay, you can go and travel in both directions. Okay, or you can say that 0 and 3 are adjacent to each other. Okay, of course, I can also have directed edges. Okay, so example is here, directed edge that goes from 3 to 4. Okay, so in this case, we'll say that 4 is a neighbor of 3, but 3 is not a neighbor of 4 because you cannot get from 4 to 3 using this edge, but you can go from 3 to 4. Okay. Next, the edges can have weights. For example, this undirected edge here from 1 to 2 has a weight 7. Of course, directed edges also can have weights. Okay. And you can also have the vertices connected in a loop like this. So 0, 1, 4, they are connected in a loop. Okay, this loop is called a cycle. We'll talk about that more later. Okay, so this is the basic definition of a graph. Okay, you have your vertices, you have your edges. Okay, and the graphs that we'll be looking at is basically a simple graph, meaning that it's not a multi-graph. What's a multi-graph? A multi-graph is one where between two vertices, I can have multiple edges connecting them. Okay, for example, let's say between 4 and 5, I can have multiple edges connecting them of different weights, for example, each one different weight. So we won't deal with this kind of graphs. Okay. So, but there is one kind of multi-graph that we might be looking at. Okay, one kind only. Okay, so disclaimer, not all. We won't. I'm not saying that we won't look at all multi-graphs. Okay, but we might look at one type of multi-graph, which is this. Okay, number one, bidirectional edges. This edge can go like that, or it can go like that. Okay, bidirectional edges. Okay, that's the only multi-graphs we'll look at. Okay, in fact, if you think about it, an undirected edge can be represented as a bidirectional edge because it allows you to travel in both directions. Okay? In fact, that's how we will sort of represent them in your graph data structures later on. Okay. Okay, so it's graph. Okay, so actually graphs are used everywhere. Okay, they are used to model lots of things. Okay, so it's a very useful data structure, abstract data structure. Okay, so now social networks are very prevalent, right? So you have lots of social networks. You have Facebook, Twitter, Instagram, LinkedIn, Google Plus, whatever. I don't know what's the latest one. So that's why we are still using Facebook for our group, for our 2010 group. Okay. Some people tell me it's outdated already. Facebook is outdated. Okay. Okay. So how are things represented in a social network? Okay. Basically, each person in your social network, I can represent it as a vertex. Okay, as a vertex, right? And then if one person is a friend to another person, I can link them with an edge, undirected edge. Correct? Yeah, because friendship is two-directional, bidirectional, right? So link them with an undirected edge. Okay, so you can get a network like this, get a graph like this. Okay. So have you heard of this particular theory? It's called 6 degrees of separation. Have you heard of that? 6 degrees of separation. What does it mean? It means that if you try to link up everybody on Earth, right? That means that, okay, if you know this guy, okay, so everybody is represented as a vertex. Then he said, if you know this guy, then there's an undirected edge, right? So I can represent everything as a graph, right? Yeah. So the theory is that I start from one guy, and I just need to move through 6 vertices. At most 6 vertices, I can reach everybody in the world. Okay, so that's called 6 degrees of separation. Okay. I don't know whether that's true or not. I don't think someone has done a really large-scale experiment to test this theory out. Okay, but based on anecdotal evidence, it seems to be true. Okay, it seems to be true. Okay. So, graphs are everywhere. It can be used to represent, for example, social networks. Okay, next, more graph terminologies. Okay, more graph terminologies. Okay, that's the notion of sparse graph versus dense graph. Okay, sparse graph versus dense graph. Okay, so sparse means this: the graph does not contain so many edges. Dense means it contains many edges. So you see that it is not a very accurate description. Actually, that's the way it is. It doesn't have a very strict. Okay. Dense, sparse, and dense does not have a very strict definition. Okay, it does not say that the number of edges must be a certain ratio of the number of vertices or something like that. No such thing. Okay, so there's no guideline how many. Okay, but for example, okay, this graph here. So for example, this graph here, okay, on your right. Okay, this is a sparse graph. You can see it's more or less a sparse graph, right? Correct. And then the one below it, it must be a dense graph, right? The one below is actually a complete graph, okay, where one vertex is actually linked to every other vertex. Okay, so this is called a complete graph. So if you have v vertices in a complete graph, how many edges do you have? You have v choose 2 number of edges, okay, which is the maximum number of edges you can have in a simple graph. Okay. So what is another example of, okay, you know dense graph is definitely, complete graph is definitely a dense graph. So what is another example of a sparse graph? Is a tree a sparse graph? Tree should be a sparse graph, right? Because it is the smallest graph that will connect every vertex. Yeah. So you have v vertices, how many edges do you have? V minus 1 edges, yeah. Another example of a sparse graph, a totally disconnected graph. You only have vertices but no edges. That's definitely sparse. Okay. Okay, so you have sparse graph, you have dense graph, then you have complete graphs, and now you have notion of the in and out degree of a vertex. Okay. So in degree of a vertex is how many edges are pointing into the vertex. Okay, that's in degree. And then out degree is how many edges are pointing to the vertex. How many edges are pointing to the vertex? Okay, that's in degree. Out degree is how many edges are pointing out of the vertex. Okay. So in an undirected graph, the in degree and out degree of a vertex is basically the same. It's simply the number of edges that is adjacent to the vertex. Okay. So in this case, for the sparse graph here, you see that for 5, in and out degree is 3. Yeah. But for directed graphs, okay, it's different. Like I said, in degree, number of edges coming in, out degree, number of edges going out. Okay. More graph terminologies. Okay, that's the notion of a simple path in a graph. Okay, so what's a simple path? It's simply a sequence of vertices connected by a sequence of edges. Okay, sequence of vertices connected by a sequence of edges, and there are no repeated vertices. Okay, that's where the symbol comes from. There are no repeated vertices. Okay, so if you have a path, then there's also the associated notion of a path length or path cost. Okay, so in an unweighted graph, the path cost or path length is just the number of edges in the path. Okay, so in the weighted graph, it's the sum of all the edge weights. Okay, in the path. Okay, then associated with the simple path, you also have the simple cycle. Okay, so a simple cycle is simply a path that starts and ends with the same vertex. Okay, so only the start vertex and end vertex is repeated. Okay, no other vertices are repeated. Okay. Okay, so let's look at some examples of this. Okay, here I have the MRT system. Okay, MRT system map of Singapore. Okay, so if you take a look at this, this is a transportation network, right? You can see that I can represent this as a graph. Right. So what are the vertices in this graph? It will be all the MRT stations, right? Each MRT station is a vertex. Okay, what are the edges? Edges are those that connect adjacent MRT stations, right? Right. And it's bidirectional. It's an undirected edge, right? Because you can go in both directions. Okay. So, in this, in the graph representation of this MRT network, what's the example? What's an example of a simple path? Okay, something like this. For example, if I have, I'm trying to get from Clementi all the way to Outram. Okay, so start from Clementi, go all the way to Outram here. Okay, this is an example of a simple path. Yeah, so you have some vertices, which are the MRT stations in between Clementi to Outram, and then you have the edges that connect them. Right? And then no MRT station is repeated, so this is a simple path. Okay, and then you have the notion of the length. Okay, the length of this path, which is just the number of edges. Okay, in this case, there are how many stations? 1, 2, 3, 4, 5, 6, 7, 8. 8 stations. Okay, from Clementi to Outram. So there are 7 edges. Okay, so the length of this simple path is 7. Or you can say it's 7 hops. Okay, so this is a simple path. Is there a notion of a simple cycle here in this network? Is there an example of a simple cycle here? Yeah, you have. You have quite a few actually. So example is here. Okay, this is the Sengkang LRT West Loop. Okay, so you can start from here and then go all the way and then come back here to this point. Yeah. So this is a simple cycle. Okay, so there are no repeated edges, no repeated vertices except for this vertex here. Okay, so simple cycle. Now question, is there an example of a non-simple cycle here? Oh, where? Which one? The yellow one. Is this an example of I need to trace it out. Can you tell me how to trace it out? Then I can get a non-simple cycle. Okay. Yellow one is like that, right? And then after that, wait, let me see. Can I go like this? Oh, wait. Let me change color. Where's my red? No conflict with that. Okay, let me use this one. Okay, let me trace that. Like that, like that, like that, like that, like that, like that. Then after that, where can I go? this is okay. You mean just the black part? The black part is not a cycle. That's a path, right? It's actually a path. This is not a cycle. Cycle, you need to have all the vertices in a loop. Yes, I want a non-simple cycle. This is not even a cycle. This is a path. Yes. So is there a notion of a non-simple cycle here? You have. This one. This one is a non-simple cycle. Why, for example, let's say I start here. Let's say I start here. Okay, then I can go like this, right? I go like this here, then I go like that. I go like that, then I go like that, then I go like that. Right? So you see that, okay, this starting point here is repeated 2 times. But then this point here is repeated multiple times, right? So this is a non-simple cycle. This is the idea of a non-simple cycle. Okay. Okay, so there are many other real-life applications of graphs. Okay, you can use it to model, for example, internet and computer networks, okay, which is very obvious. So all your computers or your routers and your hubs, they are all represented as vertices, right? And then the communication channel between them, they are the edges. Okay. Next, you can also represent communication networks, okay, with a graph. Okay. So, for example, the aircraft communication network. So your aircrafts, your satellites, your control towers, okay, in your airport, they're all represented as vertices, and the communication channel between them are represented as the edges. Yeah. Same thing, broadcasting network. Yeah, so you have the satellites, you have your satellite dishes and all that, right? So all those are vertices. And here again, the communication channel between them, those are the edges. Yeah. Okay, so what other networks can you model as a graph? So I've got transportation network, I've got communication network, I have your internet. Shipping networks, all those. Yeah, delivery networks. Yeah, all these, yeah, they can be represented as a graph. Okay, next one. Graphs are also very useful when we deal with optimization problems. Okay, so it's usually for a lot of optimization problems, we can model the problem as a graph and then solve it as a graph problem. Okay, so this one is closer to computer science. Okay, so one example is this. It's called the graph coloring problem. Okay, so it's not called graph, it's called the map coloring problem. Map coloring. Okay, so what is a map? Okay, you all know what's a map, right? So you have the map of the world and things like that. So in math or in computer science, a map is just simply a plane, okay, that is divided into contiguous regions. So example is shown here. Okay, so this is a plane. So they're all divided into contiguous regions. Okay? And what you want to do is this. The map coloring problem is that I want to color the map, or I want to color the region so that no 2 adjacent regions have the same color. Okay? So that's the map coloring problem. Now, what is the optimization problem here? I want to use the minimum number of colors possible. It optimizes so that I need to use only the minimum number of colors. Okay? So actually this problem was posed in the 1800s. And nobody could solve it. Nobody knew what is the minimum number. Okay? Is there a minimum number, or does it depend on the graph itself, the map itself, right? Okay, so it's only up until like 1976 that it was solved. How? They solved it as a graph problem. So what did they do? They model this map as a graph. Okay? So every region here will be modeled as a vertex. And then if 2 regions are adjacent, then they are linked by, okay, so every region is modeled as a vertex, and then if they are adjacent, the region are adjacent, you just link them with an edge. Okay? Then it becomes, from a map coloring problem, it becomes a graph coloring problem. Okay, how do you color the vertices of your graph so that no 2 adjacent vertices have the same color? Okay? And then they discovered that actually you only need 4 colors. So this is the 4-color map theorem, okay, or the 4-color theorem. Okay. So this is another example of the usefulness of graphs. Okay, so here you have the map of the United States. Anyone from the US here? Oh yes, one. So here's one possible coloring, okay, of the map of the United States. You can see there are just 4 colors: red, green, yellow, blue. Red, green, yellow, blue. Yeah. So just using 4 colors, I can color this so that you see no 2 adjacent regions are the same color. Okay. Okay, there are more graph terminologies, but let's take a short break. Then we will come back. Okay, let's take a 5 to 6 minutes break, then we come back. Okay, let's continue. Let's continue the lecture. Okay, but before that, I have an announcement to make. Okay, you know, next week is not just your written quiz, right? You still have your online quiz, correct? During the labs. Okay? So online quiz will be during the labs next week. And I said that online quiz, you have to answer certain questions, a certain number of questions, and a certain time limit, and then the difficulty has to be hard. Okay, so until this point, right, you only can select easy and medium, right? Correct. So now hard is in. Okay, so now you can train on hard mode. Yeah, okay, so you have got a week plus one more day, okay, to train on hard mode, okay, for your online quiz. Basically, let me just give you some more details. Okay, online quiz is like this. Okay, this is the mode you will be in when you do online quiz. 20 questions, 35 minutes, hard. Okay, but you do this during lab. Okay, do this during lab. So please go for lab on Thursday. Okay, please go for lab. Okay, let's come back. Okay, let's come back to the lecture. Okay, let's go through more graph terminologies, okay, and definitions. So there's the idea of a component of a graph. Okay, more terminologies. Component. What's a component? Okay, a component is basically a group of vertices in an undirected graph. Okay, it must be an undirected graph. Okay, in an undirected graph, they can visit each other via some path. Okay, so look at this example here. In this graph, I have three components actually. You take a look at it. Right. If I look at this component that contains the vertices 0, 1, 2, 3, 4, you can see that any of these vertices here can visit any other vertex, right, via some path. Right? For example, if 0 wants to visit 4, I can go from 0, 1, 3, 4, right? I can go 0, 1, 2, 3, 4, and so on and so forth, right? But there's some path that a vertex can take to reach any other vertex in a component. Okay? So that's a component. So this definition only applies to undirected graphs. Okay, how about the equivalent in a directed graph? In directed graph, you call this the strongly connected component. Okay, strongly connected component. But we won't be dealing with strongly connected components. Okay? We only deal with components. Okay, next, there's the notion of a connected graph. Okay? A connected graph is basically an undirected graph with just one component. Okay? Meaning that any vertex in the graph can reach any other vertex in the graph via some path. Okay, so that's called a connected graph. Okay? So is this a connected graph? It has three components. It's not a connected graph. Why? Because there are some vertices which are unreachable from some other vertex. Okay, so that's the notion of reachable or unreachable vertices. Okay, so in a component, every vertex is reachable, right, from any other vertex. But if let's say I want to get from 1 to 5, I cannot, because there's no path for me to get from 1 to 5. So 5 is unreachable to 1, and of course 1 is unreachable to 5. Yeah. Next, there's the idea of a subgraph. Okay, what's a subgraph? A subgraph is basically a subset of vertices, okay, with their connecting edges of the original graph. Okay. So of course, the example of subgraph will be a component. For example, in this subgraph, I have three components, right? So any one of these components is a subgraph. Okay. But a subgraph need not be connected. Okay, I can also pick this. Vertex 1, vertex 3, vertex 7, vertex 6, and then vertex 5. Okay, so 1, 3, 7, 6, 5, and then these two edges. Okay, this is a subgraph. This is a subgraph of this graph. Okay, so it's any subset of vertices and their connecting edges. Okay. Next, more terminologies. Okay, so you have the notion of a directed acyclic graph, okay, or what you call a DAG. So a directed acyclic graph is just a directed graph. It's a directed graph that has no cycles. No cycles. So example is given here on the right. So you look at this directed graph, there are no cycles, right? You cannot find any cycles. Okay? A cycle would be something like this. If, for example, I have an edge like this. 1, 2, 3, go back to 1. So that's a cycle, but you don't have a cycle here. Okay? So, okay, next, yeah. So this is a directed graph, so I can show you example of in degree and out degree here for a directed graph. So for 0, you can see that out degree is 2. What's in degree? 0, because there are no edges pointing to 0. Yeah. Okay, then for 2, in degree to 2 is 2. Out degree is 1. No, 2 also. Yeah, because there's one edge going to 3, one edge going to 5. Okay. Okay, next, you have the notion of a tree, which I have already talked about. Yeah. So a tree is very simple. It's different from the binary tree or the binary search tree I've learned so far. Okay, the only requirement for a tree is that it is a connected graph. Okay, where E equals to V minus 1. Number of edges equals to V minus 1. That's it. Okay. Or a tree, you can consider it the smallest connected graph. The smallest connected graph. Okay. So there's only one unique path between any pair of vertex. Okay. Next, you have the notion of a bipartite graph. So this is a bipartite. Okay, this is a tree, obviously, and then this one is a bipartite graph. Okay, so a bipartite graph is an undirected graph where we can split or partition the vertices into two sets. Okay, so that the edges do not, so that you don't have any edges within the set, but you have edges. You might have edges that cross the sets. Okay. So example is here, right? 5, 1, 7, 2. There are no edges within the set. Okay? And then this one, 8, 3, no edge within the set. But you can have edges that cross the sets. Yeah? 5 to 8, 1 to 8, 1 to 3, 7 to 3, 2 to 3. Okay, so this is a bipartite graph. Okay, so now we have talked about most of the graph terminologies we'll need, and then if we need more, I will introduce them in the lectures the specific lectures, okay, where we need them. Okay, now that we have introduced graphs, we must have some way to store a graph, right? Correct. So a graph is just an abstract structure. Okay, so we need somewhere to store a graph. Okay, so now we'll look at three very basic graph data structures. Okay, three very basic graph data structures. Okay, first one, the adjacency matrix. Okay, so the first way to store a graph is the adjacency matrix. So it's very simple. It's just a 2D matrix. Okay, 2D matrix of size V times V. Okay, V by V. Okay, where V is the number of vertices you have in your graph. Okay, so every cell ij of your adjacency matrix will contain the value 1 if there exists an edge from I to j. Okay, otherwise it will contain 0. Okay, so for weighted graphs, ij, the cell ij will contain some weight instead of just binary 0 or 1. Okay, so let's look at this example here. Okay, I just blow it up so we can look at it. So in this graph here, this will be the adjacency matrix that stores the graph. Okay, so the rows here, I have 0, 1, 2, 3, 4, 5, 6. So there are 7 rows because I have got what? 7 vertices, right? So 7 rows, 7 columns. So 7 by 7 adjacency matrix. Okay, and then you see that I have an edge from 3 to 4, right? So I have an undirected edge that connects 3 to 4. So if you go to row 3, you look at column 4, it will be 1. Okay, and of course, this is undirected edge, right? So there must also be a connection from 4 to 3, right? So you go to row 4, go to column 3, and you see it's also 1. Okay. So everything else, if there is no edge between them, it's 0. So for example, there's no edge between 0 and 4, right? So I go to 0, I go to 4, yeah, it's 0. Okay. That obviously, if I go to 4, go to 0, it's also 0. Okay. And So it's a very simple way of storing your graph, the adjacency matrix. So what can we do? Okay, we have not learned any graph algorithms yet, but are there some simple graph queries that we can perform just using this adjacency matrix? Number one, I can ask whether there's an edge that connects I and j, right? Correct? So how do I do that? Just go to row I, go to column j, see whether it's 1 or not, right? Or whether it's bigger than 0 or not. If it's bigger than 0, then there's an edge. Otherwise, it's 0. Otherwise, there's no edge. Yeah. So this is what O1 time, right? Very fast, O1 time. Next, I can list down all the neighbors of I. Can I? I can list down all the neighbors of I, right? For example, I want all the neighbors of vertex 3. What do? I go to row 3, right? Then I scan through the entire row. And then I just output all the columns, which is 1 here, right? So those are my neighbors because there's an edge between them. Okay. So what's the time for this? I will scan through the entire row, right? The entire row is length v, right? So it's OV time. Yeah, it's OV time. Okay. Anything else we can do with it? Okay. Check whether there's an edge between I and j. List down all the neighbors of j of I. Answer how many vertices there are in the graph. Also very easy, right? You know the dimensions of your adjacency matrix, then you know how many edges, how many vertices there are. How about answering how many edges there are in your graph? How do you do that? You have to scan through your entire adjacency matrix, right? Count how many ones there are. Yeah. Then this one will take what time? Scan through the entire adjacency matrix. Big O V squared time, right? Because that's the dimension of your adjacency matrix. Okay? Yeah. Okay, so let's come back. Okay, we have not gone through any graph algorithms, so I mean, we can only answer certain simple graph queries given an adjacency matrix. Okay, so we know the time complexity for these. Next, let me introduce space complexity. Okay, it's very useful. Space complexity. So space complexity is basically the amount of space that you need to use to store this data structure. Okay, so for adjacency matrix, obviously it's V by V, right? So the amount of space you need is big O V squared. Okay, where V is number of vertices. Okay, so you will see that actually adjacency matrix can use up a lot of space. Correct. For example, if let's say I have got 1 million vertices, is a adjacency matrix a suitable data structure? 1 million by 1 million, I think most of our personal computers don't even have enough memory to store it. 1 million times 1 million, that's a lot. Okay, so this is where the second graph data structure comes in, which is called the adjacency list. Okay, so the adjacency list, it's sort of like a compressed kind of adjacency matrix. Okay, so instead of, you see that for adjacency matrix, right, every row, you look at the row, it represents each vertex, correct? Right? And then each row, each vertex is associated with V number of other vertices, right? You scan the columns, number of columns, right? Correct? But then not all of them are neighbors of this vertex, correct? Some of them are 0, some of them are 1. Okay? So for adjacency list, what you do is that I don't store everything. Okay, for each vertex, I don't store every other vertex. I only store the neighbors. So you actually sort of compress your adjacency matrix. Okay? So for adjacency list, what you have is just an array, okay, of size V. So each entry in this array is basically a list that stores your neighbor. That's it. Okay? So for vertex I, adjacency list I will store the list of I's neighbor. That's it. Okay? So what information do we need to store for the neighbor? It's just a pair information. Okay, your neighbor and then the weight of the edge that connects you to your neighbor. Okay? So for unweighted graphs, we can still use this pair information. We'll just set the weight to either 0 or 1. Okay, 0 means I don't use any weights, or 1 to show that it's a unit weight. Okay? So let's come back here, look at the same graph again. So this is how it will be represented in an adjacency list. Okay, Okay, as you can see, the adjacency list now is much smaller than my adjacency matrix, right? So I still have, okay, 7 nodes, 7 vertices, so I still have 7 rows. Okay, that's the size of my array. But then for each row here, each row is not size 7, right? It only stores the neighbors it has, okay, for that particular vertex. So for example, for entry 2, okay, so go to index 2, here it only stores neighbors 0, 1, 4, right? Because come here, 2, I only have neighbor 0, neighbor 1, and neighbor 4, okay? So it's a, sort of like a compressed version of your adjacency matrix, okay? And the convention we have in VGAlgo is this. We store the neighbors in ascending vertex number, okay? In order of ascending vertex number, okay? So, same thing. If, for example, there's an edge, undirected edge, right, that links 0 and 2. So you go to index 0, you find that 2 is the neighbor, right? 2 is in the neighbor list. You go to 2, you find that 0 is also in the neighbor list. Okay, so it's represented 2 times this edge, if it's an undirected edge. Okay? Right. Okay, so let's go back here. Same thing, what is the space complexity now for your adjacency list? Well, you expect it to be better than adjacency matrix, right? Yeah, so in general, it's like this, big O of V plus E. Why big O of V plus E? V is because I need the array of size V, right? And why E? Because each entry has got one neighbor list, right? Correct. So how many neighbors in total do you have? It's equivalent to number of edges, E. So total space you need is V plus E. Okay? So E is number of edges. But the problem is that in a complete graph, E is what? Number of edges is, just now we said complete graph has got how many edges? N choose 2 edges, right? N choose 2 is actually V choose 2, which is actually V squared. It's bigger than V squared. So for a complete graph, or very dense graph, E can be bigger than V squared. So for very dense graph, you find that space complexity is no better than adjacency matrix. Okay. So now you know the usefulness. When you have a dense graph, right, you probably want to use an adjacency matrix to store it. Here, a sparser graph, okay, you know that E cannot be anywhere near to big O V squared. Then use an adjacency list to store it. Okay? Or you can say this, V plus E is the maximum between V and E. Okay? Maximum between V and E. Okay, same thing. Let's do the simple graph query on an adjacency list. How do I find whether I and J are connected? So I need to go to index I, right? Then search through his entire neighbor list, right? Find whether J is my neighbor or not, right? If J is my neighbor, okay, then there's an edge between I and J. Okay, otherwise there's no edge. So what's the time? In the worst case, it can be ON, right? Because I can be connected to every other vertex. So that's ON times. So this is worse than for adjacency matrix, which is O1 times. I just use I, J, index the cell, and then I know. Okay, next. List down all my neighbors. This one is very simple. You just go to the index, okay, representing the vertex. Just go through your neighbor list, right? You list them down. Okay, so in general, it will be faster than the adjacency matrix. If number of neighbors is not close to ON, OV, okay? Otherwise, if I'm connected to every other vertex, then it's still OV type, okay? Next, finding number of vertices in your graph. Just look at the size of array list, right? Of my array list, correct? Adjacency list. Next, find number of edges. Find number of edges. Yeah, you have to go through the entire list and then get the size of each of your neighbor lists, right? Sum them up. So that's the number of edges. Okay, but this one is not big O V squared. Because getting the size of your neighbor list is just a one time, right? And I just go through the entire array, use OV, so it's OV time. Okay, it's faster than for adjacency matrix. Okay. So that's the second graph data structure. So this is the last graph data structure, which is the edge list. Okay. So edge list is very simple. It's just an array that stores all the E edges in your graph. Okay, it's a very simple data structure. So for each edge, okay, edge list I will store an integer triple, okay, which is like that, uv and the weight of the edge that connects u to v. Okay. So for unweighted graph, basically the weight will just be 0 or 1. Okay. Okay, let's go back to the example here. Okay, so same graph again. Let's look at the edge list. Okay, so here I have got 0 and 1. Edge is 0 and 1, correct? So I will store 0 and 1 here. Okay, you can imagine that because this is an unweighted graph, right? Everything here is 1, 1, 1, 1, so on and so forth. Okay, so it's integer triplet. So I have 0 and 1, so 0, 1. Next I have 0, 2, so I have 0, 2. Next I have 1, 2, so I have 1, 2. I have 1, 3, so I have 1, 3, and so on and so forth. Okay. Now, in adjacency matrix and adjacency list, because it's an undirected graph, right, we store the edge 2 times in both directions. But for edge list, we will try to reduce the amount of storing required. Okay, if it's an undirected edge, we simply need to store it in one direction to represent it's an undirected edge. Okay, in this case, what we do is that we just put the smaller vertex number first, and then we put the larger vertex number. Okay, which is why 0, 1, I don't represent 1, 0. I just represent 0, 1, that's it. Okay. And you will see that for the edge list, we sort them first by the first vertex number, the convention that we apply, and then we sort them by the second vertex number. Okay, so this is edge list. What's the size? What's the space complexity for edge list? That's big O of E, right? Because you need to store all E edges. Yeah. So can I answer same simple graph query? Find whether I is connected to J. Can, right? But I need to scan through my entire edge list, correct? To check whether I is connected to J. Yeah? So that's big O of E time. How about finding who are the neighbors of a particular vertex? Is it easy to do it with an edge list? Not easy. Yeah, you find it's not easy. Okay, you still have to scan through the entire edge list to know that. Okay. How about asking how many vertices there are in my graph from an edge list? Also very hard. Yeah. Okay, what you can do is that when you add your edges in, keep track of the largest vertex number. Well, that is, if we use this convention, we always number our vertices, right? From the smallest to the largest, like that. Okay? Otherwise, it's very difficult. You have to scan through your entire edge list also. Okay? How about answering number of edges? Oh, easy. This is the size of your edge list that gives you the number of edges. So that's easy. Okay. So it seems like edge list is not so good for answering many of these simple queries. It's only good for answering how many edges. Yeah. But it's also useful. Okay, it's still useful. We'll see its usefulness in some applications later on. Okay, so yeah, space complexity, big of E. Okay, so just for you to remember, E can be V squared. So in the end, this can also still be big of V squared. Okay, yeah, let's talk about the Java implementation for all these 3 different graph data structures. It's very simple. For adjacency matrix, you just declare a 2D array. Yeah. So for the adjacency list, you just define an array list of an array list. Okay, so you have an array list. Okay, then each entry in your array list is another array list. Okay, so what do you store in this array list? It's basically an integer pair. Okay, so int pair. AIR. Okay, int pair. Okay, so hash list basically just an array list of integer triples. Integer triples. Okay. So this will be the implementation we adopt. Okay. So because we need integer pair and integer triples quite a lot, so we can define a class for integer pair or integer triple. Okay. And for your for this integer pair class, because we will need to for the rest for a lot of these applications that we're going to go through, graph applications, we will need to compare the vertices. Okay, compare the vertices or compare the edges. Okay? Or sort the vertices or sort the edges. Okay, so we will implement the comparable interface. Okay, implement the comparable interface. Okay, so for the integer pair, of course, I have got two attributes which are integers, the first and second. Okay, and since I'm implementing the comparable interface, I need to implement this compare to method. Okay, where you pass in another integer pair to compare to this integer pair. Okay, so what you do is that first you compare whether the first attribute is the same or not. Okay, so I use the equals, dot equals method to compare that. Okay, I think you all should know this, right? Don't use not equals. When you use not equals, what are you doing? You're not comparing the value. You are comparing the references. Okay, so here I want to compare the values or the content, okay, of that integer object. So you should use equals. Okay, so if it is not equals, then I just return this. Okay, this dot first minus whole dot first. Okay, so this is convention. If this object is bigger than the object you're comparing with, it should be more than 1. More than 0. If it is equals, it's 0, right? If less than, then you return some negative number. Okay. Else, if these two are equal, then compare the second attribute or the second field. Okay. So this is how it's done. Okay. So this is integer pair. So integer triplet is similar to integer pair, except that it has three attributes, first, second, third. Okay. So you can just extend it from this integer pair class. Okay. So, yep, that's basically it. Okay, summary for this lecture. We have looked at the union find disjoint set, or UFDS. Look at the different operations on this union find disjoint set. And we've gone through a lot of graph terminologies and then also why we need to learn graphs. Because you can model a lot of problems, a lot of real life problems as graphs. Okay, and we talked about how to store this graph information in computer memory. So there are 3 different graph data structures to look at. Okay, so just to remind you, okay, written quiz and online quiz includes this lecture. So it will include UFDS and it will include your basic graph DS. Okay, so yeah, that's it for today.